So a rate law shows the relationship between the reaction rate and the concentration of the reactants. When we looked at the concentration versus time curve, the rate was the slope of the line at every point, and the rate kept changing, right? So a rate law shows us how the reaction rate is related to the concentration. As the concentration changes, the rate changes, and this is called the rate law. So here, the variable K is known as the rate constant. N is the reaction order. A is the concentration of the substance that we're interested in, and the rate is the rate. And this would be for a very simple reaction where we just have one reactant and it's producing some products. The number of products doesn't matter. So there are three orders that we will learn about. Other orders are possible. A zero order or relation, n equals 0. And so when n equals 0, we just get the rate is equal to k, a rate constant, because anything raised to the 0 power is 1. So the rate then is independent of the concentration of that reactant. In a first order reaction, n equals 1, and then the rate is directly proportional to the concentration. Oh, I know what the problem is. No, I don't know what the problem is. And the rate is equal to a constant times the concentration. So the rate is directly proportional to the concentration. In a second order, n equals 2. You see a pattern here? Zero order, 0, first order 1, second order 2. We're not trying to be confusing. The rate is proportional to the square of the concentration. So if n equals 2, the rate is equal to a constant times the concentration squared. Any questions? So other orders are possible. You could have a third order. You could have a 3/2 order, a 1/2 order. Any fractional orders are generally small whole number fractions. You're not going to find like 13/15 or something silly like that. So in this graph, we are looking at reaction concentration versus time. So here's the concentration of our reactant as a function of time. And the graph we looked at on Monday looked more like this. It had a definite curve to it. A first order reaction and a second order reaction are both going to have a curve in them. The zero order reaction is going to be a straight line. With a straight line, the slope of that line is always the same. The rate is always the same, regardless of the concentration. For both the second order and first order, the slope of the line changes as the concentration changes. So if we look at the rate versus the reactant concentration, here's the rate in molarity per second, and for a zero order reaction, where the rate is equal to k times a to the 0, which is just k, it's a straight line. It doesn't change. For a first order reaction, this is going to have a slope equal to that rate constant, and it's going to be linear. For a second order, we've got the concentration squared, and so this is an exponential function. Any questions? So in a zero order reaction, the rate is independent of the reactant concentration. Mentioned that already. The rate is just equal to the rate constant. So how does this work out? These sorts of reactions occur when the amount of reactant that's available for reaction is not actually changed by changes in the overall amount of reaction. So an example of this is sublimation. So you pretend that this is like iodine or something, and it's going from the solid state to the gas state. In order for it to sublime, only the molecules on the surface can sublime. And the rate is going to be, could possibly be related to how much surface area there is. But as this sublimes and goes away, the surface area is not significantly changed, and so the rate remains constant. Because when you get rid of one layer of particles, there's another layer right underneath, and that one can sublime. Does that make sense?
So basically it's going to sublime the same amount of times.
It's going to sublime at the same rate until it's all gone.
Because the surface area is equal to each other.
Because the surface area essentially isn't changing.
Okay,
Yeah. First order reaction, we have direct proportionality. So the rate slows down as the reaction proceeds because the concentration is decreasing. So if A is smaller, K is a constant, then the rate is smaller. So as the concentration goes down, the rate gets slower. In a second order reaction, it's proportional to the square. And so here the rate is even more sensitive to concentration. So here's a conceptual question. So looking at a particular reaction where you just have one reactant forming products, if we double the concentration of A, the reaction rate doubles. What is the order of the reaction? First order. How do we figure that out? Well, if we think about the rate laws, rate equals K, rate equals K times the concentration, or the rate equals K times the concentration squared. This is the one, the first order, where the rate is directly proportional to A. If we double A, we double the rate. Here, if we double A, we are going to quadruple the rate. In a zero order reaction, if we double A, what happens to the rate? Stays the same, okay? Well, how do we determine the reaction order? This can only be determined by experiment. You cannot look at a chemical equation and say, oh, that's a first order, or oh, that's zero order. It can only be determined by experiment. There's a couple of different methods. One method is called the method of initial rates. So here we have an initial rate that's measured when the reaction is run, and we're going to start with different concentrations of reactants. And as we change the starting concentration, we're going to see how that affects the rate. So in this example, when the concentration was 0.1 molar, the initial rate was 0.015. When we doubled the rate to doubled the concentration to 0.2, the rate changed to 0.03. When we double it again from 0.2 to 0.4, the rate changes from 0.03 to 0.06. So you can do this in a more fancy, elegant way, or a more, just kind of almost counting on your fingers way. I'll show you the counting on your fingers. So if I go from here to here, I'm multiplying by 2, right? And going from here to here, that's getting multiplied by what? By 2 also. These numbers are pretty easy because you can know that 30 is twice 15. Sometimes they're ugly and you actually have to get your calculator out. And then going from here to here, I'm also doubling. And from here to here, 30 to 60 is also multiplying by 2. So this tells me, however I change the concentration, the rate changes in the same way. They are directly proportional. So what's the reaction order? It's first order. And then it says determine the rate constant. Well, what's the rate law for a first order reaction? Rate equals K times the concentration of A. So we could pick any of these 3 reaction experiments or trials. Here's our concentration, there's our rate. So the rate is 0.015 molarity per second equal to K times 0.10 molar. And so if we rearrange and solve that, we get 0.015 molarity per second divided by 0.10 molar. And I believe that'll give us 0.15. And then what are the units going to be? Per second. So the molarities cancel out. And so I can write this 0.15 over second. I can say 0.15 per second. Or I can call it 0.15 s to the minus 1. Or I guess you could also say 0.15 1 over second. Make sense? So here are the results of a similar experiment for 0 order, starting with the same concentrations. At 0.1, it was 0.015. At 0.2, it's 0.015. At 0.4, it's 0.015. Doesn't matter what this concentration is, the rate's always the same. Over here, again, we're doing the doubling of the concentrations. So this is times 2, and this is times 2. What's the relationship between 60 and 15? Times 4. If that doesn't jump out at you, just take 60 and divide by 15. This is 4. And from 60 to 240 is also times 4. When this doubles, that quadruples. This change is this change squared. So that's a second order reaction. That make sense? So sometimes we can look at the data and do the, kind of the kindergarten method and just look at it and figure it out. Sometimes it's not as obvious, and sometimes you get some weird reaction rates, reaction orders that are like 3/2 is super hard to figure out this way. So then we have this equation here. And let me show you how that works. So we know that the rate is equal to the rate constant times the concentration to the n power, right? That's the definition of a rate law, definition of rate. What we're trying to find out is what is n. So what we can do is take the rate at one set of conditions, so concentration 1, and divide it by the rate at a different set or a different concentration, Does the rate constant change? No, because it's a rate constant. It stays the same, right? So the rate constants cancel out. So let's use this one and the bottom one. So this will be the first one. So the rate is 0.015 molarity per second, and that equals concentration of A, 0.10 molar raised to the n power. And the second one, I'm choosing to use this third line here. The rate is 0.240 molarity per second. And there the concentration was 0.40. It's also raised to the power of n, because n doesn't change either. Oh, I left out the m molarity. That's better. So now we've got something where the variable is an exponent. You're going to run into a fair number of exponents in this class. And there's logarithms too. So just, steel yourself. We can simplify this. That is equal to the quantity 0.10 molar divided by 0.40 molar. The whole thing raised to the n power. There's a little section in the appendix at the back of the book that gives you all the rules for exponents, because those things are really easy to forget. So knowing that you can do this is something that I would not expect you to remember right now. So now what we can do is we can solve this left side. So 0.015. I spilled soda on this calculator. I really should just throw it away and get a new one. The buttons are crunchy. I forgot my good one at home. 0.0625. What are the units on that? This quantity here. There aren't any. The molarities cancel and the seconds cancel. So this is unitless. And that's going to equal this thing, 0.1 divided by 0.4 is 0.25. What are the units there? No units, they cancel out again. Raised to the n power. So sometimes the numbers are such that you can look at this and see what it is. But, personally, I don't know what the square or the something else of 0.25 is. So we can use logarithms. If I take the logarithm of both sides, actually, let me do this up here. So the log of x to the y is equal to y times the log of x. So taking the logarithm allows you to pull the exponent down from its perch to where you can deal with it. So if I apply that to this here, that means that n times the log of 0.25 is equal to 0.0625. I'm going to change colors because this is getting a little bit messy here. So 0.0625 equals 0.25, n times the log of 0.25. And it's been 2 years since I did this in the classroom, and I messed up. I forgot to take the log of the other side. So if I take the log of this side, I have to take the log of that side also. And this is just leftover. So we're trying to find out what n is. So the log of 0.0625 divided by the log of 0.25 is equal to n. Now, it's tempting to rewrite that as the log of 0.0625 over 0.25, but you better be very certain of your log manipulations before you try anything like that. It's easier to just use your calculator. I'm going to take, there it is. Oops, 0.0625, log of that, divided by 0.25, log of that, equals 2.
Is there a way to put n in your calculator? Or like, is that a thing?
That's an excellent question.
I don't know.
So, a TI-36X Pro and a lot of other calculators will allow you to type in an equation and solve for the equation. And so, yes, you can do that. I'm not going to do it in class, but the important thing here is that you can solve for the variable, and if you use your calculator to do it, that's fine with me. This is not math class, right? We need to be functional in finding the variable. So if you want me to show you how to let the calculator do that for you, I'm happy to talk to you about that, but not during lecture. Any other questions? So we're going to see a fair amount of stuff like this, where we're really doing algebra on equations to solve them. Okay? Some of you might be a little rusty on that, or you may have felt like you never really understood it in the first place. Please just ask me, okay? Because I forget stuff too. Look, I just made a mistake. We just need to refresh our memory. And sometimes you never had a teacher that really explained it so that you could understand. And I appreciate a challenge. So challenge me to explain it to you so you understand. Because once you see it, it's easy. But we need to be able to manipulate things using algebra to be successful in the class. So what are the units for the rate constants? I'm going to show you how you can figure this out. You don't need to memorize it. The unit of a rate. What are the units of rate? Molarity per second. So what I'm going to do is I'm going to take this equation here and I'm going to put units in for everything I know the units for. So the rate is molarity per second. The rate constant is what I'm trying to find the units for. The unit for the concentration is molarity to the 0 power, so that goes away. So the unit for the rate constant here is just molarity per second. As in Chem 1A, be careful how you make your capital M's. And let's remember, capital M is equal to moles per liter. Is not the same as moles. Somehow it seems, especially over Christmas break or summer break, that all just gets all fuzzy in students' heads and they come back and they do some interesting things with units. So we can do the same thing here. The rate has units of molarity per second. That's equal to a rate constant, don't know the units, times the concentration, where the units are molarity. Here, that's raised to the 1 power, so it's not going to go away. There's different ways of thinking about how you arrange this, but I see that there's a molarity on this side and a molarity on that side, so I can cancel them out. But I have to replace the numerator with something. It doesn't become S, it's 1 over S. So here the units for the rate constant are 1 over S. Again, rate is molarity per second. Rate constant, we don't know. Here's molarity squared. We're going to have some like really messy looking units. So what if I write it out this way? I'm going to divide that by molarity squared. I'm going to divide this side by molarity squared. So this is a compound fraction. This is the same as molarity per second times 1 over molarity squared. So this m cancels one of those m's. And I end up with second and molarity both in the denominator. 1 over molarity second, which could also be written as m to the minus 1, s to the minus 1. Any questions? Yeah.
So for first order, can it also be S minus 1 instead of 1 over S?
It could, for first order?
Yeah.
Yes, it could be s to the minus 1. And actually, occasionally you'll see this one written as molarity times s to the minus 1. It kind of depends on how it's being written. When you're typing something in a computer, doing real stacked fractions can be a pain, right? And so then it might be easier to do it like this. Or another common thing, if you're typing, use a slash. You make it a horizontal fraction. This is really dangerous, though, because when you start manipulating those fractions, your mind doesn't recognize that this is a fraction. So let's just try to always either stack them vertically or use a negative exponent. Any other questions? Oops, got the order messed up again. Okay, the reaction A reacting to form B has been experimentally determined to be second order. The initial rate is 0.01 molarity per second at an initial concentration of 0.1. What is the initial rate when that concentration is 0.5? More than one way to solve this. Some people are good at looking at something like this and doing things in their head. And they say, oh, well, the concentration is increasing by a factor of 5. Second order means it's going to be times 5 squared. So I'll do that. If you can do that in your head, awesome. Just go ahead and do that. A lot of people can't. And so then it may be better just to be slow and steady, because in the tortoise and the hare, the tortoise always wins, right? He's not fancy or anything, but he just keeps going and he gets the job done. So one way we could solve this is to figure out what's the rate constant. They told us that it's a second order reaction. So the rate constant must be equal to the rate divided by the concentration squared. Here, I'm just rearranging this equation before I put the numbers in. 0.0100 molarity per second over 0.100 molarity squared. So crunchy. What's that come out to be? One. What are the units?
Over meters second.
Yeah, 1 over molarity times second. So now that we know what the rate constant is, we can use the rate constant and this new concentration to figure out what the rate is there. The rate is equal to the rate constant times the concentration squared. And then what happens with the units?
So, cross out.
Yeah, we've got molarity squared over molarity times second. So this guy in the denominator cancels one of those guys, and we get molarity per second. Units are your friend because they can tell you if you did something wrong. If I set this equation up incorrectly, the units wouldn't work out. I'd end up with something wonky. And for a rate, I always have to end up with meters per molarity per second. Any questions? Yeah.
Should we have to worry about any other forms of concentration being used?
Other than molarity?
Yeah.
Not for now. We will be looking at things where we're looking at the pressure of a gas. But for concentrations, unless we're just really trying to be mean, it'll always be given as molarity. So 0.250 molarity per second. So what if you have more than one reactant? So here, looking at a generic reaction, A moles of A reacting with B moles of B to form some products. The rate will be proportional to the concentration of each reactant raised to a power. That power is the order for that reactant. So we're going to use M and N because those orders are not necessarily the same. We can talk about an overall order for the reaction, and that is the sum of the exponents. So the overall order would be M plus N. And again, we cannot look at this balanced chemical equation and say what the rate law is. That'd be great, but it'd make things boring too. The rate law for any reaction has to be determined by experiment. Okay. So here we have a reaction we looked at before, hydrogen and iodine reacting to form 2 moles of hydrogen iodide. And here is the rate law. We are asked to give the overall order and the order with respect to each reactant. So what's the overall order for this one? It's 2. 1 plus 1 equals 2. Right? 1 plus 1 is 2. And the order for H2 is 1, and the order for I2 is also 1. There's one down here. 2 moles of hydrogen plus 2 moles of nitrogen monoxide forming some products. This is the rate law. What's the overall order? 3. It's 1 plus 2, which equals 3. What's the order with respect to hydrogen? 1. And the order with respect to 2. It's all caps, right? That's yelling? No! It's one of my favorite compounds. So if we double the concentration of no, the rate is going to increase by a factor of 4, provided that H2 stays the same. If we leave no alone and double H2, the rate will only double. If we change both of them, then it gets more complicated. Questions? So here's a practice problem. Considering this equation, CHCl3 plus Cl2 forming CCl4 and HCl. The initial rate is measured at several different concentrations of the reactants. So here we have concentrations of the first reactant, concentrations of the second reactant, and those are the rates that were measured. From the data, determine the rate law and the rate constant. You have to do the rate law first. So what we want to do is we want to look at one thing changing at a time. When both things are changing, it's really hard to figure out what the relationship is. But when we go, let's just number these for grins. I'm going to call this trial 1, 2, 3, and 4. If we look at trial 1 and 2, notice that the concentration of chlorine stays the same. The concentration of CHCl3 changes, and so any change in the rate is due only to the change in this concentration. How does this concentration change? What's the factor? Times 2. So then over here, not as obvious, but what's 0.0069 divided by 0.0035? It's 2, or really close. So I doubled this concentration and the rate doubled. What's the order for that one? First order. So I can start writing my rate law. So this is the answer to A. The rate law is an equation. It's not just the equals part. It's the rate equals the constant, and we just figured out that the first reactant is first order. So we could leave it without an exponent because we understand that to be a 1. Or if we want to just really reinforce it to ourselves, we could write a 1 there. Doesn't really matter. So to find the order for the other reactant, we need to find 2 trials where the CHCl3 stays the same and the Cl2 changes. So which 2 trials?
2 and 3.
2 and 3. So going from 2 to 3, this concentration stays the same, and this one does what? It doubles. So this is times 2. And this one is doing what? Well, 0.0098 divided by 0.0069 is 1.42. Well, that's kind of ugly. So we're not really recognizing what that is. So this is where we might want to use rate over rate equals concentration over concentration. So we're going to ignore this one. Well, let's just do it this way. The rate is equal to the rate constant times CL3 to the first power times Cl2 to the n power. And if I divide these, the rate constant is the same, and for these 2 that I'm looking at, the CHCl3 concentration is also the same. and CL2 to the N. The K's cancel out, these cancel out because they're the same. Oh, that didn't work very well. Okay. Trying to be clever, it's not working. So here's rate 1, 0.0069, divided by rate 2, 0.0098, is equal to the CL2 concentration to the N power divided by the other one to the N power. We can simplify this it's the whole fraction to the N power. So we've already done this math, and that was 1.42. And that is equal to 0.01 divided by 0.02, which I think is 0.005. No, 0.5. 0.5, right? To the N. What do we do to bring the N down out of its exponent? Logarithm. So the log of 1.42 is equal to N times the log of 0.5. So 1.42 log divided by 0.5, whoops, log equals, yeah, it comes out to be 0.50589, blah, blah, blah. Reaction orders are always simple numbers. You got negative? Oh, I did too. Yes.
Is this supposed to be rate 1 over rate 2? Or is it supposed to be rate 2 over rate 1? The first slide showed that it was rate 2 over rate 1.
Rate.
We've been doing rate 1 over rate 2.
So 0.0098 should be above 0.0069.
Rate 1 over rate 2, concentration 1 over concentration 2.
Does it matter if they're flip-flopped or not?
Rate 1 over rate 2, concentration 1 over concentration 2.
Basically, this is inversely left the
When you divided 69 by 98, you got a number bigger than 1?
That's what I did. Yes, thank you. See, this is what I need you guys for. I need you to keep me on my toes. So yeah, we end up with a negative rate order, and that tells us, oh, wait a minute, something's not good. So 0.0069 divided by, well, that, what, I don't know what I did there. .704.
So just to be clear, it is supposed to be rate 2 over rate 1.
It doesn't matter.
It doesn't.
You just have to have the same on both sides.
Okay.
Actually, what I'm doing is rate 2 over rate 3 and concentration 2 over concentration 3 if we're looking at these. So this over that, 0.01 over 0.02, and 0.0069 divided by 0.0098. My mistake was when I did this, I was doing 0.0098 over that because I was trying to see what is it multiplied by to get that. So now, I get 0.5. Which is equal to 1/2. So this is going to be CL2 to the 1/2 power. You can write 1/2 or 0.5, it doesn't matter. Any questions? When you can see what's happening, it's not complicated, but me making mistakes really doesn't help. So if you have any questions, please ask. Okay, yes?
So what did you do to get a positive 5?
Pardon me?
What did you do to get the 5?
What I did, so I had written 1.42 here, but 0.0069 divided by 0.0098 is 0.7, it's not 1.42. So I tried to take a shortcut and you see what happened. I essentially got it upside down, which is why there was a negative. Any other questions?
So if we got 0.5, would we round to 0 or 1? Like
0.5 is a fraction 1/2.
So, okay, so we can have fraction, it
Mhm.
doesn't have to be, okay.
You can have fractional reaction orders.
Okay.
Yeah. They're going to be low number fractions, like 3/2, maybe 5/2, but not like 17/19 or something silly like that. And the good news is, all of this stuff is problems where we're giving you the numbers and we're giving you good numbers. When you do an experiment, sometimes your data isn't very good, and then you end up with things that don't look very nice. Then you have to do it over again. Okay, so that is part of the question. What is the next question? Find K. And finding K is simpler. We have our rate law. We're going to plug in a rate and the concentrations and solve for K. And it's kind of up to you whether you rearrange the equation first or put the numbers in. I'm going to put the numbers in. So just for fun, because we haven't used this yet, I'm going to use trial 4. So in trial 4, the rate was 0.027 molarity per second, and that's going to equal the rate constant, times the CHCl3 concentration, times the Cl2 concentration, to the 1/2 power. Oops. So I'm going to take 0.027 and I'm going to divide by 0.04 and I'm going to divide by 0.04 to the 1/2 power. I don't usually use this particular calculator, and now I remember why. For one thing, its decimal point is invisible. 3.375?
Yeah.
So I'm getting K is equal to 3.375. Now, we're not going to be crazy about significant figures, but is that an extremely low number, extremely high number of sig figs? All of these things had 2, and here we've got 4. What gets a little crazy is now we're raising things to powers, and then the sig fig rules don't work as well. What are the units? It can be helpful to look at the units separately. I'm taking this, molarity per second, and I'm dividing it by molarity and molarity to the 1/2 power. So the molarity there cancels this one, and I've got 1 over molarity to the 1/2 power times second, or molarity to the negative 1/2 second to the minus 1. Ugly units, but that's what it is. Questions? One thing I recommend doing before you start doing the homework, this problem is in the chapter. This is the for practice. The example was done in the book. So look at the example, cover up the solution printed there, try to do it yourself. If you have trouble, start to look at the solution. And then do this one. And you can look up the answer. It's hidden at the back of the chapter or at the back of the book, I forget which now. And if you have trouble coming up with the correct answer, pull up the lecture video and go to this slide and listen to me start talking about it. And as soon as you're like, oh, I know what to do, pause it, right, and finish it on your own. And that way you can get practice doing these things kind of on your own, but you're not just like totally in outer space. So let's see if I got the right answer. Okay, so that one was rounded to 3.5. Second to the minus 1/2. I think that's a mistake on the slide. There's no reason for the second to be a 1/2. So here's a problem where there's not really any numbers, no calculations. So this reaction was experimentally determined to be first order with respect to oxygen, second order with respect to no. The diagrams here show reaction mixtures in which the number of each type of molecule represents its relative initial concentration. Which mixture has the fastest initial rate? So the rate depends on the concentration of oxygen and the concentration of NO. Which one does it depend more strongly on? Nitrogen monoxide, because it's squared. When I double the NO, the rate quadruples. If I double the O2, it just doubles. So what I'm looking for is one that has more NO. So in this one, here we've got 3 oxygens and 3 NOs. Here we have 4 oxygens and 2 NOs. Here we have 4 NOs and 2 oxygens. So this has a higher concentration of NO, so the rate should be faster.
Why do we need more NO?
Pardon me?
Why do we need more NO? I'm sorry.
That's an excellent question. So this is saying it's second order with respect to NO. So if we write out the rate law,
I thought that we would go slower.
it's easy to get those mixed up. Whoops. So this is squared. So whatever I do to this, it's squared. So if I double this, then the rate is 2 to the 2. Yeah. Sometimes it helps to write out the rate law and talk to yourself. We found something interesting. We're learning a lot about students as we were teaching online. I didn't use Proctorio, but a lot of people did. And students would get flagged for talking. And so then the instructor would have to review the video and realize, oh, they're just talking to themselves. They're just thinking out loud. And that makes us think, having to take a test in total silence is probably a big handicap for some people. I'm not sure what we can do about it, but it's a step, right?